Hello guys, and welcome back to another episode of chemistry. And of course, in this episode, we're going to look at optical isomerism. Optical isomerism. All right, so in the last episode, we looked at, we'll start looking into stereoisomerism. We looked at geometric isomerism. And of course, in this class, we're going to look at what? Optical isomerism. Just as a recap, we said geometric isomers are divided into two, the cis and the trans. Of course, we said a whole lot about that. If you have not watched that episode, go back and watch it too. All right. And for those of you who are fond of just watching 1 minute and running away, good luck. I wish you all the best. All right. So before we continue with optical isomerism, let us see a question from the O3 School JAMB. By the way, this video tutorial is brought to you by the one and only best O3 Schools JAMB CBT practice app. Go and look at our testimonies. Last year, in fact, a lot of people were blessed through the app. A lot of many successes, many 300s recorded. All right, so please do not slack, do not wait, do not faint. All right, download the app and start practicing immediately. I'm going to tell you more about the app later, but for now, let's see a question from the app. This is a 2011 question, number 42. All right, 2011 number 42. It says we're given work. The question is being shown on your screen right now. Okay, we're given a structure there, given a molecule, and then they say the compound above exhibits A. Say geometric isomerism, B. Optical isomerism, C. Structural isomerism, D. Positional isomerism. All right, so we're going to answer this question at the end of the class, not before. The reason why we do that is because we need to teach you first so that you understand what you are doing. Then we can now attack questions together, and then on your own, with the aid of this app, you can look for questions under the particular subtopic you have talked about, and then you can answer on your own. All right, so please let's go to optical isomerism. Okay, so like I've said earlier, optical isomerism is a type of stereoisomerism. Stereoisomerism. Okay, so I already said that before. We said that optical isomerism is a type, along with the EZ isomerism, or the one we call geometric isomerism. Optical isomerism is also an example of what? Of stereoisomerism. All right. So, of course, optical isomers have the same molecular formula. They have the same structural formula, but the difference is usually in their spatial arrangement. And that's the one who calls, some of you will say, spatial arrangement. Okay, the difference is usually in their spatial arrangement, or the orientation of their atoms in space, or the arrangement of their atoms in space. Okay, you can say the difference is in the orientation of their atoms in space, or the difference is in the arrangement, how their atoms are arranged in space. That's usually the difference. All right, and of course, a very good example is your hands. Our hands, like this as we have. Okay, this hand is a mirror image of this hand. Okay, this means, what I mean by this is that once I put this hand in front of the mirror, this is what I will be seeing. Okay, so if you put your right hand, you'll be seeing your left hand. Okay, if you put your left hand, you'll be seeing your right hand. All right, so we say they are these two hands, they are mirror images of of each other. Okay, so that means in the world of chemistry, or in the world of isomerism, we can say that our hands are they are stereoisomers. If you assume that our hands are mirror images of each other, then it means that they are stereoisomers. Okay, that they are stereoisomers. And of course, another very, very important thing that we could gain from our hands being stereoisomers is the fact that these two hands, they are non-superimposable. They are non-superimposable. Okay, what we mean by that is that they are chiral. Okay, chiral is a Greek term that means handedness or handedness, or just hand. Okay, that's what chirality means. It's a Greek term that means hand, or handedness. This means that our two hands, okay, that they are mirror images of each other, but they are non-superimposable. What we mean by the fact that they are non-superimposable is that once you take these two mirror images now, all right, and then what, you rotate them. Okay, once you rotate these mirror images, no matter how you try to superimpose them, they will never fit into each other. Let me give you an example. Like for example, if you put this hand on the mirror, if you put your hand on the mirror like this is what you'll be seeing. Like I said, if you put your hand in the mirror like this is what you'll be seeing. So if you now try to superimpose them, put one on top of the other like this, okay, you'll see that this thumb and this thumb, okay, they are pointing in different direction. Okay, as you can see, they will never ever fit. They will never ever fit. That is why sometimes if you have two hand gloves, for those of you that have been opportuned, like in my village, we don't have hand gloves. Okay, many years ago, we didn't have hand gloves. So many of you also maybe have never had an opportunity of wearing an hand glove before. But if you have been opportuned of seeing an hand glove before, or I mean glove, or the normal hand glove, okay, that you wear, you cannot put the left hand glove in your right hand. Will it fit? It will not fit. So you cannot put the right hand glove in your left hand. It will not also fit. So they will not fit each other. So that means that they are that they are non-superimposable. You cannot superimpose them together. Okay? And in the world of chemistry, or world of isomerism, we call that process we call that chirality. Okay, we say that our hands are they are chiral. They are mirror images of each other. They are mirror images of each other, but they are non-superimposable. And also we also say that they are asymmetric. We bring the term asymmetric. That means they do not have they lack a line of symmetry. They lack a line of symmetry. Okay, they lack a line of symmetry. They are asymmetric. Okay, so we are going to talk about chirality as we continue. To make you understand this better, let us use an illustration. Let's say you have a molecule like this. For example, let's say you have a molecule like this. Okay, we have carbon, then we have A, for example, at the top. Then here we have another A. Then here we have this molecule this atom, this group is going out of the page. Let's say this is B. Then we now have the one that's going into the page. Let's say this one is E, for example. All right. So if this is in tetrahedral form. Okay, tetrahedral. Okay, so this is in tetrahedral form. Okay, so if we place this molecule, in front of a mirror, what are we going to see? Let's say this is our mirror. So we'll place this molecule in front of our mirror. What are we going to see? Are we going to see our C? Okay, are we going to see our A? All right. Then, of course, in this case, this because it's in front of a mirror now, I'm going to be seeing this group in this side. Sorry. Excuse me. So I'm going to be seeing this particular group in this side. This one here, this E will be in this side. So I'm going to have this, our E. Then this one that is going in will still be going, this one that is going out of the page, rather, will still be going out of the page. And then I'm not going to have our A here. This is what I'm going to see in the mirror. All right. So this means, but the problem here is that this is the mirror image of this. One thing we can draw from here is that this is the mirror image of this. All right. But of course, the problem here is that, is this superimposable or non-superimposable? Can we superimpose these two together to fit? Okay, and of course, because we're having two different groups here. Okay, we're having two groups of the same, or we're having the same two. Two of the groups that are bonded to carbon rather are the same here. AA. Okay. AA, it means that if there's a way we can rotate this molecule so that this will fit into this. That means that this molecule that are superimposable. Okay, they are not chiral. So what we call that term is is non-chiral. We say that this molecule is is non-chiral or a chiral. Okay, we say it is a chiral or non-chiral because we can superimpose this molecule on this molecule with just a little bit of rotation. All right, because we are seeing two groups, okay, bonded to the same group, bonded to carbon atom here. Okay, but of course, now let us see another example. Let's say we now have another example. We have C again. Here we have A. Then of course here we have let's say we have B. This one going into the page. Let's say we have D. Then of course this one we have E. All right. If we place this in front of the mirror, what are we going to see? We're still going to see our C. Then, of course, we're going to see our A. What will happen? This E is coming this way, right? So we're going to see our E. Then, of course, we're going to see our D also here. All right. Then what else are we going to see? Let me make this the same. Let me say D. Let me draw my D where. Okay. Then, of course, this one now will come out this way. This is what B. All right. And, of course, no matter how you rotate this molecule, no matter how you rotate it, okay, no matter the amount of rotation you give to this molecule, it can never fit into this. You can never superimpose it on this. They are mirror images of each other. 1, 2, they are non-superimposable. Okay, because they are what non-superimposable, you say that what this molecule is what is chiral. We say that what that this molecule is what is chiral. In this first case, okay, you see that what we have what AA here. Say two groups, okay, 2 groups of the same what character in what bonded to what bonded to carbon. Okay, then we now have the 3rd group and the 4th group. Yeah, we're having what A again. EB, the mirror image is showing that. All right, so that means that what we can superimpose this on this. Because we can superimpose this on this, then we say that what this molecule is what is non-chiral or a chiral. But this one, on the other hand, is not superimposable. You cannot what superimpose this on what on this because they are what they are non-superimposable. We call that what the chiral. What to say it is what it is a chiral molecule. Okay, so this is what optical what isomerism. All right. So how do you now check for what for chirality? How do you check for chirality? How do you know that what that a molecule is what is chiral? Okay, how do you tell that what in a molecule there's a chiral what carbon? Okay, and of course that will now lead us to what chirality is. Like I said, chirality means what non-superimposable, but what it really means is that what a chiral carbon is a carbon that is what bonded to what 4 different groups or atoms. Okay, and let me make that one very, very clear. Okay, that a chiral carbon, okay, is one that is bonded to 4 4 different groups or atoms. Okay, so this is what chirality is. Okay, a chirality is what is bonding what 4 different groups or atoms to what to a central carbon atom. So when we talk about chirality, we will have a central carbon atom, then it will be bonded to 4 different groups, just like we are seeing in this case here, where if for example here was B. Okay, sorry, let's say for example here was what was here before A. Okay, let's say here was B, then here was D, here was E. Then okay, that means here will be what also what B. Then here will be what? Here will be D. Okay, these 2 what molecules? Okay, they are mirror images of each other. They are non-superimposable. But what is more is that what you can see that what this central carbon atom, which is called the chiral carbon, or we say this is what the chiral center. Okay, we can say this is what the chiral carbon or this chiral what center. It is bonded to what 4 different groups. You have A, you have B, we have D, we have E. In this case, what we mean that what A may be, for example, let's say an hydrogen group. B may be what an amino group, NH2. D may be, let's say, an hydroxy group, OH. E may be a carboxylic group, COOH. That's what we mean. So something like this, having C bonded to hydrogen, then here bonded to what? Let's say amino group, NH2, that is what? H2N. Then, for example, here we now have OH, then bonded again to, let's say, COOH. Okay, so this is a chiral what model. It is chiral because it is bonded to what? 4 different groups or atoms. That is what chirality is about. Okay, so a chiral what molecule is molecule that is bonded, that the central carbon atom is bonded to what? 4 different groups or atoms. Is that very clear? All right. So now, what next? Let us now also use what real molecules to what to give what example to make this word very, very, very clear. Okay, for WAEC students, sometimes we will be and of course, one very important thing also is that what these 2 molecules, there's a name we give them in chemistry. We will say that they are what enantiometric pairs or they are enantiomers. Okay, so we say that they are what that they are enantiomers. Enantiomers. We say that they are what? That they are enantiomers. Okay, so this is the first enantiomer, And then this one here is the what? Is the second what? Enantiomer. Enantiomers, they are what? They are optical isomers. Enantiomers are optical what? Isomers. All right. So that being said, let us now say, for example, in an exam condition, especially for those of you who want to write WAEC, okay, and of course, you may be told to what to draw what the enantiomer of a particular molecule is very, very easy. Okay, but for JAMB sake, you cannot be told to draw. Okay, you will only be told to what? To like predict, just like what we saw in the OT School JAMB app before we started the class. We were told that what this molecule represents which type of isomerism or shows which type of what isomerism. Okay, so maybe giving question can be thrown from anywhere. So you have to what? You have to open your mind to what? To learn what? All of them. They're all simple terms. Okay, so let us use what? An actual molecule to what? To explain this further. Let's say we are given 2-hydroxypropanoic acid. 2-hydroxypropanoic acid, and then we are told to what? To draw the what? The enantiomer. Okay, for example, we have what? 2-hydroxypropanoic acid. Okay, so please take note. We are going to learn how to name organic compounds. We are not just there yet. You get there, you will name compounds, you will tire. Okay, so please get the OT School JAMB app. It is there to what? To help you. It's there to help you succeed in your exam. It has all the past questions you can ever want to ask for. Has wonderful features like the question search feature, where you can search for question according to topic, and the question that JAMB has set under that topic will come out for you to answer. What is more? What's interesting, of course, is the what? The UTME challenge. The app has the UTME challenge where you compete with your mates every Saturday under normal JAMB exam condition. You select your subject and you compete with your mates all over Nigeria. Okay, you win prizes, get used to how JAMB sets their question, and of course, you build your confidence towards the main exam. The activation fee for the app is a little token. Okay, make the sacrifice, activate your app, start practicing on time so that you do know what you get. Go and look at our testimonies. You will see how this app has helped thousands of students, and your case will not be different. Go to Play Store, immediately download the OT School JAMB app. Okay, so let's just say we are giving this example, 2-hydroxypropanoic acid, and of course we want to draw what? The enantiomers. Okay, so of course this is propanoic. So from propane we know that what? We're talking about 3 carbon and 3 carbon. Okay, so I have C. I'll start my drawing like this. Drawing the structure. Okay, so having propanoic acid, so CCC. Of course, they say 2-hydroxy. That means on the second carbon there's an hydroxyl group there. So we're going to have what? OH here on this point, and then I'll talk about propanoic acid. Okay, so that means there's a carboxylic acid group there. So that means I'm going to have what? O, and then I'm going to have what? OH. Okay, so these are our 2-hydroxypropanoic acid. Okay, all right. So we're going to what? I'm going to write my H and complete my structure like this. All right, so now these are our 2-hydroxypropanoic acid. We are told to what? To draw the what? The enantiomers. It's very easy. So those of you that have not been understanding since when we started, this will be a very, very good way to what? Easily understand what you have been doing. Okay, so now for us to be able to draw what? Enantiomers, the first thing we can do or we must do is to first of all fit or find the what? The chiral carbon, or to find the what? The chiral center of what? Of the molecule. So in this molecule we are given, we have to find the chiral what? Center. We have to find the chiral carbon. And what do we say a chiral carbon has? A chiral carbon must have 4 different groups or atoms bonded to it. It must have 4 different groups or atoms bonded to it. So now let's look for the chiral carbon now. Okay, so let's start with this first carbon. Can this first carbon be the chiral carbon? Can it? It has hydrogen, it has hydrogen, it has hydrogen, and then it now has this group here. Okay, I'm going to clean it up. Okay, so this is, we're considering this first C now. Okay, so it has what? 4 groups. 1, 2, 3, 4. But it is bonded to what? 3 of the same group. So this carbon cannot be our central carbon atom because it is bonded to what? 3 of the same group. Chirality say 4 different groups. Okay, so because of that, this first carbon cannot be our central carbon atom. It cannot be what? Our chiral center. So now let us see the second. Let us see the last carbon. The last carbon here is bonded to what? This group is bonded to what? This group, and then it's now bonded to what? All of this group here. Okay, this is the third one. Okay, it is bonded to what? To 3 groups, not 4. Okay, this is the first group. This is the second group. This one here is the third group. So it is bonded to 3 groups. And for chirality, we talk about what? 4 groups or atoms. 4 groups. 4 different groups, rather. 4 different groups. Okay, so that means that also cannot be our chiral what? Center. Okay, so now which one will not be our chiral center? Let us consider this middle one. Okay, it is bonded to what? To hydrogen. It is C, is bonded to what? To hydrogen. Also, is bonded to what? This is a methyl group here. That is CH3. It's bonded to what? To CH3. So we can have what? H3C. Then, of course, it's also bonded while trying to draw it in a tetrahedral form. It's bonded to an hydroxyl group, OH group, and then it's also bonded to what? A carboxylic acid group. So we also have COOH. Okay, so this is our diagram. It's very clear that what? This is our central carbon atom because it is bonded to what? 1, 2, 3, 4. 4 different what? Groups. So we have found what? Our chiral carbon. So now the next thing we do is, so that means this is our first what? Enantiomer. Okay, this is the first enantiomer. This will be the first enantiomer. Or I can say enantiomer 1. Okay, so this is our first enantiomer. And then of course we can now what? Put it in front of a mirror. And then of course I say I'm going to have our C. Yeah, I'm also going to have our H. Then of course this COH is coming this way. So I'm going to have HOOC. Okay, then yeah, we're going to have what? Our OH also. Then of course, what's next? Then this side, we're going to have what? Our H, sorry, not H3C now, but CH3. Okay, so I will tell you why. I will tell you why here we are seeing HOOC. If you put in front of the mirror, I'm going to this is exactly what I'm going to see, right? But of course, now the problem here is that we cannot use COH here. We cannot come and write COH on this mirror image because it is not bonded to what? It is not directly bonded to what? To hydrogen. Okay? It is directly bonded to what? To carbon. Okay? So that's why I cannot say what? If we say COOH here, for example, COOH here, that means it is directly being bonded to what? To hydrogen. And that will be wrong. Especially for WAEC students. So please open your eye. So you cannot what? Draw this molecule like this. But of course, if you want to get extra mark, you should say that what? HOOC, because it is directly bonded to what? To carbon. Also here, you are seeing I'm using H3C, not CH3, because it is directly bonded to what? To carbon, not directly bonded to hydrogen. You get the drill now. So that is that for that. So we have drawn the first enantiomer, and this one will be the second what? Enantiomer. Okay, so of course this side, that is what, and that is what the first and second enantiomer. We'll be able to draw that word successfully. Hope that is clear. Okay, so now let us see one more example and then we are done. Let's say we have 1 amino ethane 1 ol. 1 amino ethane 1 ol, for example. 1 amino ethane 1 ol. Okay, so we're having this, for example. Now, 1 amino ethane 1 ol. All right, so now, if you want to draw this structure, it's very easy. So I'm giving ethane. So we know that what ethane has how many carbon atoms? 2 carbon atoms. So we want to have 2 carbon. Then of course they say 1 amino. That means our amino group what will be on the first carbon. If this is our first carbon, or this is our second carbon, or this is our first carbon, or this is our second carbon, depending on which carbon is taking priority. Okay, let's say we want to prioritize this carbon here now. Okay, that means that what our amino group, our NH2, which is our amino group, will be here, and then our what? Our hydroxy group will also be on the what? On the first 1 amino ethane 1 ol. Okay, the hydroxy group is on the first carbon atom, and the amino group is on the first carbon atom. Okay, then of course I'm going to have our H here. Then I'm going to have this H. Of course, to also draw this enantiomers is very simple. Like I said, the first thing to do is to first of all locate your central carbon atom or your chiral carbon. So which one is our chiral carbon here? Can we say it is this first one? No, because this first carbon has 3 of the same group bonded to it. Okay, so this first one cannot be our chiral carbon. That means automatically we should check this next one. This one is bonded to hydrogen, bonded to NH2, bonded to OH, and bonded to what? A methyl group. That means that this is our central carbon atom. All right. So now, if we draw that in tetrahedral form, we're going to have our C bonded to hydrogen, bonded to what? A methyl group. Then I'm going to have our OH group. Then I'm going to have what? Our NH2. Okay. So very simple as ABC. So now we can also now draw what now? The mirror image. So if I draw the mirror image, I'm going to have our C bonded to hydrogen. Yeah, I'm going to have what? H2N, not NH2 again, because it is directly bonded to nitrogen, H2N. Then here we are going to have our what? Our OH, and then here we're now going to have our what? CH3. So this is our first enantiomer. Then this one is our second enantiomer. Now, another thing we need to note here is that these enantiomers, this first and second enantiomers, they are different. They are what? They are different. You can see they have the same molecular formula, even the structure is the same. Okay, the only difference here is in the orientation of the atoms. Okay, but of course, apart from that, they are also what? Different. And how are they different? They are different because of how they interact. How they interact with plane polarized light. Okay, they are different because of how they interact with plane polarized light. Let's say we have an enantiomer. Okay, let's say we have an enantiomer, and then we pass plane polarized light through it. Okay, what will happen? Okay, let's say this is our sample of an enantiomer, and then we pass plane polarized. Why do we use plane polarized light? We cannot use anyhow light that is incident in different direction. Okay, we can only use a plane polarized light, so that when this polarized light passes through this enantiomer, when it comes out here, we will know that it is this light that came out. But let's say we use a light that is incident here, incident here, incident here, incident here, incident here, incident here. If it comes out, we will not be sure whether it is this particular one, or 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 it is this particular one, and so on and so forth. That is why we use plane polarized light. We pass light that travels in one direction. So if you want to travel in the X plane, let it travel in the X plane. If you want to travel in the Y plane, let it travel in the Y plane. But we must use a plane polarized light. Okay, so the difference between those two enantiomers is how they interact, like I said, with plane polarized light. Okay, so now let's say we pass plane polarized light through an enantiomer. As we pass plane polarized light through an enantiomer, it will come out from the other side, and it will rotate plane polarized light either to the left or to the right. Okay, so this is what happened. This is the effect. Okay, the enantiomer, they interact with plane polarized light differently. Okay, one of the enantiomer, we rotate it in a clockwise direction. This is clockwise. In a clockwise direction, or in a positive direction. Okay, then or to the right, you can see it can rotate plane polarized light, or it rotates plane polarized light to the right, or clockwise direction, or rotates plane polarized light to the left, or anti-clockwise direction. Anti-clockwise direction. So this is what would happen. So once we pass plane polarized light, a light that is traveling in one direction through a sample of an enantiomer, what we do, it is either rotate it in a clockwise direction or to the right. If it rotates it to the clockwise direction or to the right, we call that dextro-rotatory. Okay, so if it's rotate plane polarized light to the in a clockwise direction or to the right, we say it is dextro-rotatory, or we call that sample the D-isomer. The D-isomer. Okay, but if it rotate it anti-clockwise, okay, or to the left, we call that levorotatory. Okay, we say it is levorotatory, or call it the L-isomer. Okay, and of course, because it rotates it to the left, that means it's rotating it in an anti-clockwise direction. All right, so please take note of that. So the effect of the interaction of enantiomer with plane polarized light is the rotation in the clockwise direction, or in the anti-clockwise direction. All right, so we're able to effectively see the difference, okay, about how enantiomer interact with plane polarized light. But some other times, or in some other conditions, okay, once we pass plane polarized light through enantiomer, it will not rotate it. It will not rotate it to the left or to the right. Okay, I think this is right. Okay, to not rotate to the right or what, to the left. Okay, so in some other cases, once you pass what, plane polarized light through a sample of an enantiomer, it will not rotate it. In fact, the effect of the rotation will cancel out. It will not rotate it. Then that means that what, we now form what we call what, a racemate. A racemate. We now have what, a racemate, or we call it what, racemic mixtures. Racemic mixtures. Okay, so a racemate, okay, a racemate is what? Is a solution of enantiomer containing what, 50% of each what, enantiomer. So just like we're having two enantiomer, for example, first and second enantiomer, we have 50% of this enantiomer, then we have 50% of the other what, enantiomer. So we have what, enantiomers in equal proportion. Okay, so once we have enantiomers in equal proportion, or 50-50, we now have what we have what, as what we call what, a racemate. A racemate. A racemate. 50-50. Equal proportion, the same proportion. That is what, a racemate. So we now have what, a racemic mixture that is formed, and sometimes we will be able to what, to separate these racemic mixtures. If we want to separate them, we call that process the resolution of a racemate. Okay, we call that process of separating racemic mixtures resolution of what, of a racemate. So please take note of that. So enantiomers in equal proportions, okay, in the same quantity, okay, we cancel the effect of rotation, all right, and then we now have what we call what, racemate, or what, racemic what, mixtures. All right, so that is what, racemic what, mixture, that is racemate. Now, but another important thing we also need to know is that, why do we even study optical isomerism? Why? What is the importance of optical isomerism? We have said that what, we talked about enantiomers, then we talked about them what, rotating what, plane polarized light. Okay, another important thing you should know is that what, that two enantiomers may have what, different biological properties. Okay, two enantiomers may have different biological properties. For those of you that will study biochemistry, when you get to the university, you will see a whole lot about this. We are going to go deep into this. Okay, so two enantiomers may have what, different what, biological what, property when they what, pass through what, light. Okay, so for example, we have what, an example, we have what, carbon, C-A-R-V-O-N-E. Okay, carbon. One of the enantiomers of carbon has what, a mint smell. You know what a mint smell is, isn't it? Mint. I've seen mint leaf, right? Mint leaf. Okay, one of the enantiomers has what, a mint smell. The other one has a smell of caraway seeds. Caraway seeds. Okay, so that is what, one example. The other one is, so we have what, we have limonene. Okay, for limonene, okay, one has what, a citrus smell. Then the other one has a pine tree smell. Okay, so you can see they have different biological properties. Okay, they have the same molecular formula, the same structural formula, but of course their properties are what, their biological properties are what, are different. Okay, but now these ones are just, let us not talk about smell. Let's talk a very, very good example that is applicable to what, to human life. Okay, that is now the one we call what, thalidomide. Thalidomide is an example. Okay, thalidomide. Thalidomide is used in treating morning sickness. One of the enantiomers is used in what? In treating what? Morning sickness or nausea in what? In early pregnancy. Okay, one of the isomers is what? Is used in what? In treating morning sickness or nausea in early pregnancy. Okay, but you know that the other enantiomer, okay, the other isomer of it causes birth defect once it was taken by what? By pregnant women, okay, it leads to a lot of deformities in children. It can even cause stillbirth, where the baby are die since you don't even know. Okay, so many can cause many birth defects or deformations. Okay, so that one is what we call the teratogene. Okay, this one causes birth defect. In fact, it has been known to cause over 2,000 birth defects. 2,000 birth defects. So you can see. So once this is why we practice optical activity, so that you know that this particular isomer is optically active. Then you will know what the properties. See what it can do, because we do not just administer drugs how to people. All right, so that is the importance of optical isomerism. Okay, so it is because of this that we knew that this one has another isomer that causes deformations in early pregnancy, or causes stillbirth, okay, or defects, or several defects. Okay, so now having seen this, now what I'm going to do to round up this class quickly is to now tell you, we are going to give you a question. Okay, I'm going to give you a question, and then you will now decipher whether that molecule we are given is optically active or not. Okay, let us quickly jump to that part. That is the interesting part of the class. The other part has been talk. Okay, but before we do that, there are two other terms that you should get entwined with. Okay, you should get in line with. That is what we call diastereomers. Okay, or some people call it diastereomers. Okay, diastereomers are stereoisomers that are not mirror images. Okay, they are They are stereoisomers that are not mirror images of one another. That's what we call diastereomers. They are mirror images. There were stereoisomers that are not mirror images of one another. They also have another one that we call mesocompounds. Okay, mesocompounds have a chiral center. They have a chiral center. They are characterized by having a chiral center. Okay, they have a line of symmetry. They also have a line of symmetry, but they are not optically active. Okay, so within the scope of this class, this is just what you should know. I'm just adding them, so you may not really even need them in this level. Okay, but just know them, all right? Because you never know, you can never tell. All right, so please know them. But if when you get to higher institution, you are going to deal with this in a whole lot more sense. Okay, so please, that is that. So now let's quickly go to how to decipher if a molecule is optically active or not. Let us see an example. Let's say we're having this molecule C. This is 1, 2, 3, 4, 5 carbon atoms. Then let's say here we have Br. Okay, so now the first thing to do here is to test for chirality, or look for the central carbon atom. Okay, so now which one can this first one be our central carbon atom? Let us draw the groups out. Of course, this is HH. This is H, yes, H, yes, H, yes, H, yes, H. Can this first carbon be the central carbon atom? No, it's already bonded to 3 of the same group. Can it be this also? It's bonded to 2 of the same group already. Can it be this also? No, it's bonded to 2 of the same group already. Can it be this? Maybe. It may not. It may be. Okay, let us draw that out. Let's draw in a tetrahedral form. We're going to have H. Then here we're going to have How many carbon atoms we have here? C3. How many atoms of hydrogen? 1, 2, 3, 4, 5, 6, 7. C3, H7. Then here we're going to have Br, that's our bromine. Then here we're going to have now? CH3. Okay, so obviously you can see here that this one is is having it's bonded to 3 to 4 different groups. 1, 2, 3, 4. So we can say that this one is optically active. Okay, so it is optically active. So let us do another example. Let's do another example. Let's say we are having C. Let's say here we have fluorine. Okay, so the first thing, like I said, that we should do is look for the central carbon atom. So can it be this first one? Obviously, cannot be this first carbon. Okay, then here is hydrogen. Then here is Hydrogen. hydrogen. Okay, so it can also not be the third carbon. So it's definitely have to be what this central carbon atom. So here we're going to have our C, then here we're going to have our H, then here we're going to have our what H3C, here we're going to have our what our F, then here we're going to have our what CH3. Okay, so now is this optically active or not? So you can see obviously here that it's what it is not optically what active. Why? Because the central carbon atom here is bonded to what? You can see 3 of what of the same group, not 4. Because this CH3 is also here. Okay, so this one is not chiral. This is not a chiral carbon. It does not have what 4 different groups. So because of that, this is not what optically active. Let me give you one to do on your own. All right, to test your knowledge of what of followership of a commander. All right, so I, the commander of this army, give you a very good example to do by yourself. Let's say you have something like this, CH3, CH2, CHI, CH3. This is iodine I. This is iodine I. Okay, so let's say you're given that molecule is very, very what easy. So you can bring it out in the structure form and what you can be able to look for your chiral carbon and then test if it's optically active or not. If it's optically active, comment it under what the comment section. Make sure you comment, like this video, comment your questions, comment your just say something nice, okay? And what make sure you are subscribing to this YouTube channel. All right, so that is for that. So some other times you will be given a molecule, you'll be given the formula of a molecule and be told to you'll be asked to tell if it's what optically active or not. Let's see an example. Let's say we're given C6H12. Okay, so to do this is very easy also. The first assumptions you have to make is that what you have to assume that what it has a central carbon atom. Okay, you have to assume first that it has what a central carbon atom. So if you have this and then it is bonded to a hydrogen what group, then it's bonded to a methyl group, H3C. Okay, then it's bonded to also an ethyl group, CH2CH3, and then of course you can now calculate. This is your first assumption. The first assumption you have to make is that what? That it has what a central carbon atom. All right. Then you bond it to what? To an hydrogen group. Bond it to what? To a methyl group. Bond it to an ethyl group. All right. Then the last one, how do you calculate? How many carbon atoms have you used? This is 1. This is 2. This is 3. This is 4. You have used 4 carbon atoms. C4. How many hydrogen atoms have you used? This is 1. This is 1 plus 3 is 4. 4 plus 2 is 6. 6 plus 3 is 9. You have used what? 9 what hydrogen atoms. So what is left from here? Then we are left what C2, and then I have what 3 of what of hydrogen from here. So that means that what that will be the last one here. That's C2H3. Okay. So because it is bonded to what 4 different groups. Okay, you can answer that what of course it is optically active. All right, so that is the idea behind it. So first of all, you make assumption that what it has a central carbon atom. It is being bonded to a hydrogen group and ethyl group. These are the major groups, okay, that it can easily be bonded with, and a methyl group and ethyl group, and then can calculate for the last what a group that is attached to it. Okay, let us see another quick example. Let's say we are giving this, for example, C5H11Br, for example. Okay, so first thing we assume that it has a central carbon atom bonded to hydrogen. Okay, bonded to what? A methyl group bonded to an ethyl group, CH2CH3. Okay, so what will now be left? How many? Sometimes of this was C4H9. What will be left here is what? one C. Then how many hydrogen? 2. And then what? Bromine. So that means this last group here would be what? CH2Br. And of course, it means that what? It is also what? Optically active. All right. So you should try. Maybe you should try this. Try C4H10 and let me know if it is what optically what active. Okay, so thank you very much. We are glad you were able to join us and learn about optical isomerism. Please do not forget to like this video. Do not forget to subscribe to this channel. Click on that subscribe button. Okay, if you have not subscribed before, share this video to your friends and loved ones, and make sure you get the Optical School JAMB app and start practicing your way to amazing result in JAMB. Thank you for watching. I remain your commander. I will see you in the next class.